Hello, my name is Andrew, and this is my project for the Machine Learning Foundations for Product Managers course offered by Duke University. For this project, we were tasked to build a model to predict the energy output of a power plant, given 4 independent variables. And we were provided historical data tracking those variables against the power output. As we can see here, we have data for the average temperature, the exhaust vacuum, the ambient pressure, and the relative humidity, as well as the resulting data outputs. So let's first look at the modeling approach. Given we were provided continuous structured data representing past observations of features and their corresponding targets, I believe this is an example of supervised learning, and we should be doing regression. Now for feature selection, my first hypothesis is that all 4 independent variables correlate to the power output. So for the first model, I would use multiple linear regression, taking in all 4 variables. There is a small chance this model would overfit. So after creating the first model, I would evaluate the coefficients generated there and remove the one that has the smallest coefficients. Then I would take the remaining 3 features and build a second multiple linear regression model to see if it produces better results. For the output metrics, I want the mean average percentage error, or MAPE, so that I can easily interpret the amount of error from the model. I also want the mean squared error because it's good to know if and when this model spikes in errors, given that we're dealing with a power plant. And I also want the R squared value because that shows how much variability is explained by the model. Now let's look at the data splitting strategy. We were given 9,568 hourly average readings. This represents over a year's worth of daily data. I think this amount of data is sufficient and cross-validation is not needed for now. So I split the data 80-20, 80% for training the 2 models and 20% to test the chosen model. I also chosen to randomize the data when building the models. To generate the model, I used Excel's built-in regression function. And it's kind of nice because it automatically gives us the coefficients, which we can see here. Scrolling down, we also see that it automatically gives us the residuals, or the actual error values. And it also gives us the R squared for free. So given that we have the residuals, it's quite easy to calculate the MSE and the MAPE. The MAPE is the average of the sum of the absolute values of the residuals divided by the actual values multiplied by 100, and the MSE is the average of the residual values squared. Now looking at the results, like I said before, the R squared is pretty good because it's over 0.9 and pretty close to 1, which indicates that this model is good at explaining the variability. The MAPE is also under 0.8%, which I believe is quite good. And we'll need to use the second model to evaluate whether or not this MSE is a good value or not, but we have it here. But anyways, we now have the coefficients, which we can plug in to test the data when we get to that stage. Looking at the coefficients, the smallest value is the AP, which is the ambient pressure. So for the second model, we'll take the AP out of the feature set and we'll build a multiple linear regression model with the remaining 3 independent variables. here are the results. As we can see, the model also performs quite well. In fact, the output metrics are pretty much the same as the first, but they are marginally worse. The R squared is a bit higher, the MAPE and the R squared is a bit lower, and the MAPE and the MSE are a bit higher. As a result, I decided to go with the first model to test the outputs. And here are the results. Column E represents the actual output data from the test data. And column F represents the predictions that we generated using the multiple linear regression formula that we see here. Using the same approach as before, I calculated the MSE and the MAPE. And as we can see here, they are pretty close to each other. They're well within the range of each other. As predicted, they are marginally worse than the training data sets. For the R squared, we no longer get it for free. So I manually calculated taking 1 minus the total squared error, which we already have, divided by the sum of the total squared deviation from the mean. So that means we just need to manually calculate the average of the actual power outputs, and everything else we can just plop into the formula. And as we can see here, the R squared is also over 0.9, which is close to 1, and it is relatively lower than the training data, but it is well within range. Given all this information, I believe this model is sufficient to use against production data. Now, in terms of the next step, I would consider doing some cross-validation to check for overfitting. But most importantly, I would monitor how well this model performs against the actual real-world data. If underfitting is detected, I would look into adding more features into the model. If overfitting is detected, I would run a lasso regression to remove any unwanted features. Thank you for taking the time to evaluate my work, and have a wonderful day.